Hello, everyone, and welcome to my talk. I'm Daniel Morton, and I'm going to be speaking about database indexing. Now, everywhere I've worked, there's been a general lament that developers do not have a solid enough understanding of database indexing and query performance, and I'd like to do something about that. Now, all the information I'm going to talk about is readily available. There's lots of internet resources out there that can, teach you all of this stuff. But it's sometimes hard to parse through all the relevant, documentation and really understand how it all kind of fits together. So I'm kind of aiming to help with that in this discussion, discussing how the data structures apply and the patterns and really make it so you can get to understand what's actually going on under the covers, at least with simple database indexing and performance. So I'm going to be providing a whirlwind tour of the absolute essentials that you need to know to use database indexes effectively. I'll be focusing specifically on the Postgres relational database, but all the content will be broadly applicable to any traditional relational database and even some non-traditional ones. Any non-trivial application eventually runs into the need for database indexing. When you start dealing with thousands, millions, or billions of rows, a well-configured index is the only thing standing between you and disaster. When developing an application, database performance is everyone's responsibility. Anytime you introduce a new workload to the database, you should be ensuring you fully understand the work the database will be doing, how it will do it, and what the impacts of that work could be. Indexing is a broad topic and there are many trade-offs involved. There's no 100% correct way to index a database table. Often you're targeting good enough. The simpler you can make queries, the better. The more complexity you add, the more difficult it is to reason about how to optimize the execution. So, we will discuss what indexes are at a very basic level and why we need them. We'll discuss how databases decide what to do in order to give you the results you want. We'll discuss the types of indexes that Postgres has and the data structure that is used, at least for the most common index type. We'll discuss the complexities of indexes that cover multiple database columns. And finally, we'll discuss the basic tools available to discover how your queries are performing and to understand how to improve them. So, what are indexes? Well, indexes in a database are very similar to the index in the back of a book. If you want to know if a book contains a certain topic, you can read it from cover to cover, or you can flip to the back of the book, quickly find the topic in the alphabetically sorted index, and see what pages that topic is covered on. You can then turn right to those pages and find the details you want. In database parlance, reading the book cover to cover is called a table scan or a sequential scan, and reading through the index is called an index scan. The index is much smaller than the book itself and is organized in such a way that it's very fast to find what you're looking for. A database index is the same. It's usually much smaller than the table and organized in a way that's easy to find information quickly. But rather than a series of page numbers, it gives you a series of row IDs that you can then use to get the actual information you're looking for from the table. Now, it's worth noting it doesn't actually give you those row IDs. It does all that magic under the covers. You never see those row IDs, but that's how it's actually working. Now, if you don't have an index, you need to read through the entire table, row by row, and see if it contains the information you're looking for. The more data you have to read to get the information you want, the slower the process is going to be. Reading data from storage, even fast storage, can take a long time when you're talking about millions or billions of rows. Now, just like with books, every time you update the main content, you also have to update all the indexes to match. As such, indexes are not free. While indexes are designed to be read and updated efficiently, every change you make to the underlying database table requires a change to each and every index you create. I/O operations are slow, so if you have a huge number of indexes, you can easily cripple the performance of your queries that insert, update, or delete data. And lastly, just like books, if you're indexing only a very small amount of information, using an index to look it up can actually be slower than just reading the entirety of that data. Imagine you had a book that's only 5 words long. You want to know what page the word the is on. Well, you can probably guess it's on page one, but if you look, you flip to the back of the book, look at the index, and then you see that there's 5 entries in the index. You read through them and discover that the word the is on page one. Well, you then turn back to page one, and there you see the word the. It would have been faster just to read those 5 words on the first page instead of flipping to the back, reading the index, and flipping back to the front. So database indexes work in the same way because you have to do an IO operation to read each element of the index, and then a subsequent IO operation in a different part of the disk to read each row of the table you're trying to retrieve. When you execute a database query, you are describing to the database what you want to happen, not how to do it. There are many possible algorithms and strategies it could use to all reach the same correct result. The query planner comes up with all the possible strategies that it can think of, and then it invokes the cost-based optimizer, which sorts through the possible solutions, assigns a score to each of them, and then picks what it decides are the best combination of steps to achieve that goal. To do this, it uses metrics like how many rows are in the table, the access patterns like how often the table is read from or updated, and what indexes exist on the table. This is one of the reasons that it can be difficult to optimize indexes in a development environment. Having a realistic set of data is one key part, but the additional statistics around accurate table access patterns is another that is often missing from a dump of production data restored locally. The cost-based optimizer is quite smart. Some databases like MySQL allow you to override the decisions of the cost-based optimizer if you think you're smarter than it is. Postgres does not give you this option, however. Postgres is very confident that it is smarter than you are. So there are five main types of indexes available in Postgres, although in practice you'll only really be dealing with one most of the time. The default index in Postgres and most databases is the BTree, which is a good general purpose index. Unless you specify otherwise, when you create an index in Postgres, it will be a BTree. As this is the most common index you'll encounter, we'll spend a fair bit of time talking about them in detail shortly. A hash index is very similar to a hash map. It maps a specific hashed value to a specific row, so it is very fast for finding exact matches, but not good for ranges or similar kind of queries. A block range index is similar to table partitioning and is best suited for data where there's a logical ordering to the rows, like in the case of time series data. The index is broken down into buckets with a min and a max value in each bucket, and those buckets are ordered. So in this way, it's easy to find the specific bucket you need to look for and the data that is in it. A generalized inverted index is useful for searching structured data like arrays or JSON blobs. And lastly, the generalized search tree is an extensible index type that can be used with a wide variety of complex data types and has applications for things like full-text search and geospatial search. So those last four index types we're not going to talk about a lot today. We're going to spend most of our time focusing on the B tree because it is probably the one that is most relevant most of the time. So in order to determine how to optimize database queries with indexes, it's important to understand how the underlying data structure works, so you can reason about what the index can and can't achieve. So a B tree is a balanced tree where all leaves are the same distance from the root, so it takes the same number of traversals to get to any given leaf node. B trees are designed and optimized for use on data stored on disk. Each node can contain a configurable amount of keys, and when adding a key that would exceed that number, the tree is rebalanced. Usually, a node will contain a very large number of keys, enough to fit into one disk block. Although our example here is much narrower for illustration purposes, and it'll rebalance when a node would contain 4 keys. So the keys in each node are sorted, typically from least to greatest, although it's configurable when you build the index. And it's worth noting that an index, the keys are anything that's sortable. So it can be any combination of values from your database table columns, as long as they are sortable. Now, the one implication of that is you could have one column's data as part of your key that's sorted in an ascending way, and one part of your key from a different column that's sorted in a descending way. So you have the ability to configure that when you construct your index. Now, when you have a node in your B tree, there are pointers at either extreme. So on the left-hand side, you will see a pointer to another node, and you guarantee that all the keys in that node are less than or equal to the leftmost key in that node. On the right-hand side, you have the opposite extreme, where you guarantee that all of the keys in the child node on the right-hand side of the tree are greater than or equal to the rightmost key in the node. In between each key in the node is another pointer to a set of child nodes, and you guarantee that the keys in that child node are greater than or equal to the key on the left and less than or equal to the key on the right. So this example illustrates a B-tree, what a B-tree might look like for a primary key index that contains 20 rows numbered 1 to 20. One of the benefits of the B-tree is that it allows you to quickly discard large portions of the tree that you don't care about, which can make search very efficient. So we're going to look at this, look at a quick example here. So say we wanted to find the value 9 in the B-tree that we have here. So what we would do is we would look at our root node, and we'd start at the leftmost side and see the lowest key. We'd see it's a 4. So we're looking for a value 9, and we know that 9 is greater than 4. We know that all the keys in all the nodes to the left of this must be less than or equal to 4, which means we can very quickly exclude this entire subtree. So we don't even have to look at that. So 4 isn't a value we're looking for, so then we can look at the next value, and we see it's an 8. So we know 8 is also less than 9, the value we're looking for, and we know that all of the keys in the nodes between 4 and 8 must be also between 4 and 8, which means we can entirely exclude this subtree from our search. Then we look at the value 12. We see it's the last key, and we know that all of the values to the right of this key must be greater than or equal to 12. We're looking for 9, which is less than 12, and that means we can entirely exclude that portion of the tree. So we've narrowed down very quickly to the part of the tree that we're looking for. We know that between 8 and 12, all of the keys in the child nodes between those must be between 8 and 12, greater than or equal to 8, less than or equal to 12. So we traverse down. We know if the value that we're looking for exists, it must be in this subtree. So we then look at the first key in the child node, and we see its value is 10. Well, that's not right. We don't care about that. But we know that the value 9 we're looking for is less than 10. We know everything in the right-hand subtree would be greater than or equal to 10, which means we can very quickly exclude that portion of the tree. Then we navigate down the left-hand side, and we see that the one and only key is a 9. That's the value we're looking for. So then we can read the row ID that's associated with that. If we're trying to look up the data, that's associated with this portion of the index, we can go to the table, read that row ID, and get our data. If it's a primary key or a unique index where we're trying to see whether it exists or not, then we've already proven what we need to prove. So you can see we were very quickly able to get rid of entire portions of the subtree. 3 of the main branches of the tree we were able to immediately exclude, and then very quickly narrow down to the one value we're looking for. And now, earlier I mentioned that a key can contain potentially multiple values sorted in different ways. And we'll talk about that a little more when we talk about composite indexes in just a moment. But this last point is interesting. It's worth noting that indexes effectively provide sorting for free if your query pattern matches the sort pattern of the index. So if you're looking for values that are sorted in an ascending way, and your index was created in an ascending way, you don't have to do any sort of writing to disk to write temporary tables that you're doing sorts in. You can just get that sort value from the index. Now, if you have multiple columns and they're sorted in different ways, one ascending, one descending, your query pattern has to match that, has to be looking for the first column ascending, the second descending, in order to take advantage of that free sorting. So as long as your query pattern matches how your index was created, you're able to take advantage of that. All right, now we're going to look at a more concrete example. So we have a table here called flights, and this table tracks flight data. So what airport a flight leaves from, what airport that flight is destined to, the ID of that flight, the alphanumeric code, what plane is going to be flying on that route, the airline, and the takeoff time. So a pretty straightforward table, and we have 20 rows inserted into it. You can see for our from airports, we have 4 represented, YUL, YVR, YYC, and YYZ. And we have 4 different plane classes involved as well: 777s, 767s, 747s, and 737s, and 2 airlines, WestJet and Air Canada in this case. So as we mentioned a little bit earlier, when you only have a small number of rows in a database table, The cost-based optimizer will usually just read that table directly from the table itself. It's not going to bother using an index because it's less efficient for it to go back and forth. So we're going to pretend that we have thousands of rows in this table for purposes of our example, so that we can see what it looks like when we actually use the index involved. All right. So we're going to consider 7 different queries here on this table, and we're going to use a specific index. That index is going to be called from airport plane class index. It's going to be on the table flights, and it is going to be based on the columns from airport and plane class in that order. Now, one thing I wanted to mention is, as much as the order of the columns in the index very much matters, from airport and plane class in this case, the order in the where clause that you were using to filter by does not matter. So you can put your where clause conditions in any order you want. It makes absolutely no difference to the actual execution of the query plan. So that's important to remember. So we have our index, and we have a BTree that has been built using that index. So you can see we have a composite index that contains 2 parts. So the from airport is the first part of the key, and the plane class is the second part of the key. And then we have a pointer to the row ID. That points to the actual row in the actual table. These numbers are just made up, but they all correspond to the insertion order of this data in this case. So this one down here that points to 1 was the very first row inserted. Row up here was the 11th row inserted, for example. So the first query we're going to look at is a query that shows us equality on the left index column. So we're doing select flight ID from flights, where from airport is YUL. So we are looking for all of the nodes, all the keys in this BTree index that contains YUL. So you remember from our earlier example how we navigate this. We look at the root node and we look at the first key, and we actually only have 1 key in this particular node. And we see YVR is the very first part of it. Well, we know that everything to the right of this one node is greater than YVR, and we know that everything to the left is less than or equal to YVR. I should say greater than or equal to YVR for the right, and less than or equal to YVR for the left. Now we're looking for YUL, and we know that alphabetically YUL is earlier than YVR, which means everything in the right-hand subtree cannot possibly start with YUL. So we can immediately cross out that whole part of the subtree. We don't care about that. So YVR obviously isn't what we're looking for, so we navigate down the left-hand side. We look at the very first key, and oh, look, we see YUL. That's fantastic. So that's a node we're looking for. We don't care what the plane class is. We're only filtering on the airport. So we can just note, yep, that is one we want. We see ID 16 there. Now, we know that we're looking for YUL, and any nodes further to the left of this must be less than or equal to YUL. They may be equal, however, so we have to navigate down and see what's actually there. We navigate down, we see YUL 737. Well, that is one we care about. We care about YUL. So we note that row. That's fantastic. We're out of keys, so we navigate back up and look at the next key here. We see YUL 747. YUL is also one we're looking for. That's great. So we found another one. And now we know that all the nodes between here and here, the first key and the second key, must be YUL, because the left one is YUL and the right one is YUL. The only way for there to be more keys down there is if they are all also YUL. So we have to navigate down because we actually need the ID. So we do have to walk this part of the tree, but there's no way any of these nodes, any of these keys in this node could possibly be ones we're not looking for. So that's great. We found all of those. We navigate back up, move on to the next key. Now we see YUL 777. Hey, that's also one we're looking for. That's great. We note that. And again, much like our previous traversal down, we see the middle key is YUL and the right key is YUL. That means all the keys in the subtree down here must also be YUL. So we traverse down, we're guaranteed that they're all ones we want, so we note their row IDs. Then we jump back up here, and we know that anything to the right of this node, YUL 777, must be greater than or equal to this. Now, it could be another YUL that's also a 777. Or it could be something that is a different airport entirely, one that's alphabetically later. So we have to go down the tree and take a look. We go down, we see YVR. Well, we don't care about that. That's not one we need. So we can jump back up and we've navigated all the relevant portions of the tree now. So we found our 8, 9 nodes that we care about, and we were able to do so by eliminating one entire section of the tree. So we only had to go down half of it. And now, as it turned out, a good chunk of this tree actually contained what we were looking for. But if it didn't, if only a couple keys were YUL, we would have been able to quickly eliminate big chunks of that tree. So that shows you that very efficiently you can find all the keys that you need when you are doing an exact match on the leftmost column in the index. So we'll back out of that. All right, let's move on to our second example. This is where we have equality on both index columns. So we're going to do select flight ID from flights, where from airport, the first column is YYZ, and plane class, the second column, is 747. So again, we go to our root node and we see YVR is the first key in that node and the only key in that node. Now, we know that YYZ is alphabetically later than YVR, and we know that everything to the left in the tree must be less than or equal to YVR. That means we can entirely exclude this entire subtree. That's great. So we've cut off almost half of the tree. Now, this isn't a node we're looking for, obviously, it's YVR. So we have to navigate down the right-hand side of the tree, and we look at our first key in this subnode. We see YYC. Okay, that's interesting. So we know that YYC is less than YYZ alphabetically. So we don't need to look at the plane class yet. We know that everything to the left of this must be less than or equal to YYC, so we can immediately eliminate that portion of the subtree. This node, or this key, isn't one we're looking for, the YYC. So we move on and look at the next one. We see YYZ. Hey, that's fantastic. And then we look at the next part, 747. That matches what we're looking for. Great. This is a node that we want. Excellent. Now we know that everything to the left of this middle node and everything to the everything to the left of this middle node must be less than or equal to YYZ. Everything to the right of this YYC must be greater than or equal to YYC. So it's entirely possible we have some more YYZs down this subtree. We navigate down, we look at the first one. Oh, we see YYZ. That's great. Now we look at the next part of the key, and then we see 737. Well, we're looking for 747, so we don't care about that node. We then move on to the next one, and we see it's also YYZ. Excellent. And hey, it's a 747 as well. That is one of the ones we're interested in. So we note that, and we've looked at all the keys here. We navigate back up. Now we look at the next key. We see YYZ 767. Okay, well, we're still in the right ballpark, YYZ. However, 767 is greater than 747. That means that we don't care about this particular key, and everything to the right of it must be keys that we're not looking for, because they must be greater than or equal to 767s. 747s are obviously less than a 767. So we entirely get rid of that portion of the subtree. Great. We then know that there may be YYZs between these two YYZs, so we navigate down and we see YYZ. Excellent. This is in the right ballpark again. And look at the next part of the key, 747. Exactly what we're looking for. So we note that, and we've now examined the entire tree that we have to. We've discovered row 4, 5, and 9 are rows we care about, and we were able to eliminate very substantial chunks of the tree that we never even had to walk through. So also very efficient to look up all of the keys in an index when you have equality on all of the columns in it. We're going to move on to the third example, which is equality on the rightmost index column. So I suspect you all can see where this is going. We're looking for the flight ID from flights where a plane class is 737. So plane class is that second column there. So as usual, we go to our root node and we see YVR. Well, that's not that useful because we're looking for 737s. I don't know what to do with that. So, maybe this is a 737. I don't know. We have to look at the next part of the key. We look at the next part, 767. So yeah, we don't care about this node. That's not, not a node that we want, but we have no idea which portion of the subtree that more 737s could be down, because the first part is sorted by airport code. There could be 737s in both parts of the tree. So we have to start by going down the left-hand side. We see YUL. Well, that's still not meaningful to us. We're only looking for 737s, but then we look at the next part of the key. Hey, it's a 737. Okay, so that's good. We found one that we're looking for. And then we navigate down the left-hand side of the tree because, again, we have no idea. Same as before, we don't know. There may be a different airport, the same airport, any sort of airport down any side of the subtree that maybe may have 737s at it. We don't know. So we navigate down here and we see YUL. We don't know whether that's relevant or not, but we also see 737. So that is one that we care about. Great. We navigate back up and move on to the next key, YUL 747. Okay, so we don't care about the airport, but we see this is a 747, so we don't care about that key. So that's good at least. But yeah, between YUL 737 and YUL 747, we have some subkeys. They could be 737s because they have to be greater than or equal to 737 and less than or equal to 747. We know they're all YULs, but we don't care about that. So we navigate down, look at the first key, see YUL 737. Okay, great. We want 737s. That's good. We look at the next key, YUL 737. Yeah, we want that one too. Great. And then look at the third one, YUL 737. Yeah, also one we want. So that's fantastic. Back up, and then we move to the last key, YUL 777. So it's the same problem we've had before. Down the right-hand side, there could be a different airport that is alphabetically greater than YUL that has a 737. The fact that it's a 777 doesn't mean anything to us. So we have to navigate down this part of the tree, and we see YVR 737. Okay, we don't care about YVR, but 737 is one we care about. Now you'll notice I actually skipped a step. I did that intentionally. So you see this key, we have YUL 747, and this key, YUL 777. So we actually know, just from looking at this, that nothing down this part of the subtree could be a 737. Now, because we know it's greater than or equal to YUL and less than or equal to YUL, they all must be YUL airports. So that's a good thing to note. And then we see the less than or equal to the greater than or equal to 747s, but less than or equal to 777s. So we are actually able to exclude a portion of the subtree there because we know that none of those keys could possibly be a 737. So we had a little optimization there. We walk back up to the root node, and again, we have to go all the way down. So I'm not going to walk through this entire example because it's exactly the same. As the first part of the tree we looked at, we can't exclude any particular part of the subtree except in a very rare circumstance. We have to, because we have the airport first, we have to walk through pretty much the entire tree looking for 737s. Now, it's a little more efficient than doing a table scan because this has much less data, um, but it's not nearly as efficient as our previous example because we were able to cut out large swaths of the tree where we're just not able to do that when our index is our where clause is on the very last column there. So we'll back out of that example. And on to the fourth. So this is interesting. We have two inequalities on the same column. So in this example, we have select flight ID from flights, where from airport is greater than YUL and from airport is less than YYZ. So we're looking for any airports that exist in between there. So again, we look at our first part of our node, or the first node, the root node, and we see that our first value is YVR. So YVR is greater than YUL, so this satisfies that condition, and YVR is less than YYZ. Great, so this actually is one of the rows we're looking for. Fantastic. Now, we know that everything to the left of this node, of this key on the tree, must be less than or equal to YVR. There may be some more YVRs down here though, so we have to navigate down the tree. So first of all, we look at this key and we see YUL. Well, that is not greater than YUL, so we don't care about that node. And we know that everything to the left of this node must be less than or equal to YYL, which means we can entirely exclude that node without even looking at it. We look at the second key and see it's YUL as well. Everything to the left must be less than or equal to YUL, and we're only looking for greater than YUL, which means we can entirely exclude that portion of the subtree. Next, we move on to this, the third key, and we see it's also YUL. We're looking for greater than YUL, which means we can entirely exclude that portion of the subtree because we know everything between there must be YUL. Now, our last key is YUL. We know everything to the right must be greater than or equal to YUL. We don't know whether it's YUL or something else. So we have to navigate down and we see, oh, it's YVR. That's actually one we want. So we note that row ID. Excellent. Then we walk back up the tree and then we have to walk down the other side. So then we look at our first key and we see YYC. Well, that is less than YYZ and greater than YUL. So that's great. That's one we want. And it is, we also know that anything less than, or anything to the left on the tree is less than or equal to YYC. So it could be YYC, could be YVR, could be something else. So we are going to navigate down and we see it's YVR. That's one we care about. So we note that. Jump back up. And then we go to the next node and we see YYZ. Okay, so we're looking for less than YYZ, and we know that anything in between these two keys must be greater than or equal to YYC and less than or equal to YYZ. So it's possible the child node here has some keys that we're interested in. So we navigate down and we see the first one is YYZ. Well, we don't care about that. We're looking for less than or equal to YYZ. So we know that everything to the right of this spot on the tree must be greater than or equal to YYZ, which means we don't care about this. We don't need to look at that anymore. And we don't care about anything over here. So we're able to immediately exclude anything that's over there because we know that anything past here on the right, past this middle key, must be greater than or equal to YYZ, and anything past here on the right must be greater than or equal to YYZ. So we've been able to get rid of substantial swaths of the tree by filtering on two inequalities, the greater than and the less than. So we've been able to demonstrate that with that fourth query that inequality conditions on the same column, multiple inequality conditions on the same column, can be very efficient. Excellent. So now let's look at the fifth query. And here we're selecting flight ID from flights where airport is greater than YVR and plane class is less than 767. So two inequalities, but this time on different columns. So like before, we look at our root node and we look at the first key in it, the first and only key. We see that it is YVR to start. Well, we're looking for greater than YVR, so we don't actually care about this particular key. And we know because of the nature of the tree that every key in every node to the left of here must be less than or equal to YVR, which means we can immediately exclude this entire portion of the subtree. Fantastic. Okay, so now we're back at that the root, and we have to go down now the right-hand side because we know everything to the right must be greater than YVR. So we're greater than or equal to YVR anyway. So we walk down the tree and we look at the first key, we see YYC. Well, that is greater than YVR. So, okay, we're in the right ballpark, but now we're looking for planes that are less than 767. So then we move on to the next part of the key and we see, oh, it says 767. We're looking for less than. So this is not a key we care about. Now, we don't know any more information about what's further down the tree because anything to the left of this must be less than or equal to YYC. So it could be YYC, and it could be a 767, could be a 737, could be anything. Anything that is less than or equal to this particular key. So we have to walk down the subtree, and we see it says YVR. So we don't have to look any further into the key. We know this is not one we want because we're looking for greater than YVR. So we walk back up the tree, and then we look at the next node, and we see it is YYZ, the next key rather. We see it's YYZ to start, which is greater than YVR, so that's great. This might be what we're looking for. And our next part of our condition is less than 767. Well, 747 is less than 767. So that's a node we want. Excellent. So now we know that all of the keys in children between these two keys down here must be greater than or equal to YYC 767 and less than or equal to YYZ 747. However, it's entirely possible there are other airports down there So we have no idea really whether we have to look down here or not. So we have to walk down and find out. We see the first key is YYZ 737. So YYZ is greater than YVR. That's great. And we have 737, which is less than 767. So that satisfies this particular condition. So we're able to note that. Excellent. Now we move on to the next key and we see YYZ 747. YYZ satisfies our greater than YVR and 747 satisfies our less than 767. So we're able to note that. So it's fortunate that both keys down here were actually ones that are relevant to us, but there was no requirement for it to be the case. It's entirely possible there could have been another YYC 767 down here that we wouldn't have wanted. So we just got lucky that we had, all the keys down here are ones we wanted. We navigate back up. Now we know everything to the right of here must be greater than YYZ 747, and we're looking for less than 767, greater than YVR, so we don't know any really additional information yet. We look at the next key, we see YYZ 767. Well, we're looking for YVR, which is less, or looking for greater than YVR. YYZ satisfies, but 767 does not. So we do not take this particular node because it does not satisfy our condition. Now we know all of the children nodes must be greater than or equal to YYZ 747 and less than or equal to YYZ 767. It's entirely possible there's another YYZ 767 down here. We know both any child keys must be YYZ, but we don't know what planes they are. So we have to navigate down and take a look. We do so, and we see YYZ 747. Well, that is a row we care about, so that's great. We note that and walk back up the tree. Now, we have YYZ 767 here. We are looking for anything greater than YVR, so YYZ satisfies, and we know that any airports further to the right of here will satisfy this. And we're also looking for plane classes less than 767. We know everything to the right of here must be greater than or equal to YYZ 767. However, we do have to walk down the tree. It's entirely possible that there is a YZZ further to the right with a 737, for example. That would match. So we have no way of being able to filter that out. So we walk down our tree and we see YYZ 767. Okay, well, that's not what we're looking for. It is greater than YVR, but it is not less than 767, so we don't care about that. And we have to look at the next node because, again, it could be YZZ 737, something along those lines. Turns out it's a YYZ 777, which does not satisfy our condition. So we are done examining this tree, and you see we're only able to actually eliminate a small portion of the tree based on that first check that was making sure it was greater than YVR. The fact that it was less than 767 didn't really help us eliminate anything. We had to still walk through this entire right-hand subtree to be able to look for these values. So it didn't help us eliminate anything. It did make it faster, though. We didn't have to walk through the entire table. Once we walked through all of these small values in the keys, we're able to identify which rows we wanted and then actually go to the real table to fetch the full values. So it does improve performance, but it doesn't let you eliminate big chunks of the tree, which is the real performance boost that you get from indexes. We'll back out of that example and move on to our second last example here. This is equality after inequality. So we're looking for from airport greater than YVR and plane class equals 737. So we have an inequality on the first condition and an equality on the second condition. Now this is going to look very similar to actually the example we just looked at before. So we're looking for greater than YVR. So that means when we look at the first key here, we're able to entirely eliminate the left-hand tree. So that's great. Now it's not a 737, obviously, so we don't care about this node. This key, we move down to the right-hand side. We know everything must be greater than or equal to YVR. So every airport on the right-hand side is going to satisfy our condition, but we have to look for that 737 specifically. So again, we look at YYC. Well, that satisfies. 767 doesn't, however. Now we have no idea what's down this left-hand side here. Could be a 737, could be a 747. We don't know. So we have to go down and look. YVR satisfies. 737 does not. So we walk back up, look at the next key, YYZ 747. That also doesn't satisfy. And we, again, don't know. We have no information about what's in between these. Could be a lot of different airports. Some of them could have 737s, some would not. We have to look down and we see YYZ 737. Okay, well, that's a row that we're interested in. So we note it, move on to the next key, YYZ 747. Well, we don't care about that. So we walk back up, move on to the next key. We see YYZ 767. So this is one case where we actually can eliminate a little bit anyway, because we know YYZ and YYZ are these two keys. Everything in between must be YYZ. Then we see 747 is the next part of the key. 767 is the next part of this key. So obviously 737s can't be found in there. Then moving on to the right-hand side, we know that anything to the right of here must be YYZ or greater, and greater than YYZ 767. But again, it's possible there's a YZZ 737 down there somewhere. So we have to go down and take a look. We navigate down, we see YYZ 767, so we don't care about that. And we navigate to the next one, YYZ 777. So no 737s down there. So we were able to find the one row we cared about, but we were only able to eliminate one chunk of the tree and one little node over here. So you can see that the equality portion was very useful in getting rid of nodes and keys that we didn't need to look at, but the inequality condition following it was not useful at getting rid of additional keys. Okay, so we will back out of that. And one last example. So we're going to do something a little bit different. Instead of flight ID, which is actually found in the real table itself, we're going to select plane class, which is actually something we have in this index. So we're going to select plane class from flights where from airport is YVR. So this is relatively straightforward after the examples we've seen so far. We see YVR. Oh, that's great. That's a node we care about. So we'll note that. There may be YVRs to both sides, so we have to go take a look. We go down here, we see YUL. Well, that's obviously less than YVR, means we can eliminate that. We don't care about that. Everything between these two YULs we don't care about because we're looking for YVR, and anything between these two YULs we don't care about, we can eliminate that. To the right of this key, there may be a YVR, so we have to navigate down, and we do find one. So we note that, walk back up, and over, and down the other side, and we know everything on this side must be greater than or equal to YVR. We look down here, we see YYC. Okay, well, that gives us some useful information. We're looking for YVR, which is less than YYC, and that means everything to the right of this key on this subtree must be not rows, not keys we're looking for, because YVR is less than this. So we don't have to look at any of those. We can eliminate that, and that. That's great. We do have to look down the left-hand side, though, in case it's a YYC or a YVR or something else. We look down, we see, oh, it's also YVR with a 777, so we care about that one. So that's great. So it was really easy to find those three. We were able to eliminate a good chunk of the tree. What's interesting about this example, though, is that all of the data that we need to return plane class actually exists in the index. In our previous examples, we were returning flight ID, which does not exist in the index. So we had to go look up the row in the actual table by the ID that we pulled out, and then look up that flight ID. Now here we have plane class, so what we can do, this is called a covering index. This means that the information we've gotten from the index is enough to satisfy the query. We can actually return right now without having to look at the actual table itself. So a covering index is one that gives you all the information you need to satisfy the response of the query. So you don't actually have to go look at the underlying table itself, which can be a substantial performance improvement. So in our last example, we illustrated a covering index, an index where all the data required to generate the result set was present in the index itself. Now, because of this, there was no need for the database to actually read the real rows in the table. It could build the result set from the index and return it directly, which is a very efficient operation. Often we want result sets that contain several columns. And it's not always practical or useful to include all those columns in the index, as we may never filter on them. And as part of Postgres 11, a new feature was added to indexes in the form of the include clause. Now, this clause allows you to store any arbitrary column data along with the index so that you can more easily take advantage of covering indexes. This extra data doesn't have to be sortable and doesn't have to respond to traditional equality operators, so it could be normal columns, could be a JSON blob, could be binary data. If the columns requested in the result set can be satisfied by the combination of the columns in the index and the columns in the include clause, then the entire result set can be generated from the index. The data in the include clause will not be used when determining the key position in the B-tree, so it will not generally affect lookup performance. It will a little bit, but in a way that's not too significant. Storing more data in the index means fewer index entries will fit onto a single disk page, meaning disk I/O will be less efficient. Beyond reading index data, though, it will affect insertion and update performance, as the extra data needs to be written into the index on every mutation operation. It will vary on a case-by-case basis as to whether that performance hit is worth the gains you may achieve by not having to read data from the actual table, though. So covering indexes are great, except when you want to use one in an MVCC database. MVCC stands for multi-version concurrency control, and it is how databases like Postgres handle the isolation and consistency portions of ACID compliance. When a transaction modifies a row in a table, rather than actually updating the data stored on the disk, the database writes a brand new copy of that row and tracks which transactions see which version of the row. Eventually, the old rows are no longer visible to any transaction, and they just sit around taking up space on the disk until they are purged in a process called vacuuming. So it's important to note, though, that indexes don't know about MVCC. So even if you have covering indexes where all the data you need for a query is in the index, you can't be sure that all the rows your index identifies are actually visible to your current transaction. This means that after you use your index to identify which rows you need, you have to go to the actual table and examine the data that indicates whether the row is visible to you or not. Now, this obviously defeats the purpose of a covering index because you still have to examine the table itself. Fortunately, Postgres has some hacks to make covering indexes possible under some circumstances. So Postgres maintains a visibility map for each table that tracks areas of the table that are guaranteed to be visible to all transactions because they contain rows that haven't been updated in a certain amount of time. If your index is a covering index and the visibility map indicates that all the rows you're returning will be available to all transactions, then only the index will be used without traversing to the actual table. So you get the benefit of having a covering index. One final consideration with MVCC is that for the reasons that we talked about regarding covering indexes, it also makes counting slow. Indexes can speed up count operations because they help you narrow down the particular keys that you're looking for so you can identify the particular rows that you're trying to count. However, you don't know whether those rows are actually visible to you or not. So after you've identified them in the index, you have to actually go look up again in the table itself whether those rows are visible or not. And again, that visibility map can help with that to some extent, but because you don't have that concrete knowledge of visibility of rows from the index, a lot of count operations are often not particularly performant. So ideally, if you can avoid explicit counts, it's a good idea. If you're really concerned about performance, particularly on large tables, and there's a number of strategies you can use to try and approximate rows in a table. But that's beyond the scope of what we are talking about today. So we've discussed single column indexes and composite indexes. We've discussed how querying against the leftmost column in an index is very efficient, but skipping the leftmost column and filtering by a later column is not. The generalization of this is that when using a BTree index, you are able to filter out portions of the index based on filter criteria with equality operators on the leftmost columns and the first inequality operator on a column without an equality operator. So for example, if you have an index that has three columns in it, A, B, and C, you can filter on equals A, equals B, and equals C, and that's great. You can filter on equals A, equals B, greater than C, and that's great. But if you were to filter on greater than A equals B, then filtering on the greater than A is good, but the equals B doesn't help you cut down parts of the tree. Additionally, if you skip the A entirely, so if you just do equals B, then you're not going to be able to cut down portions of the tree, as we saw in the examples we did when we walked through the BTree. So when you have multiple queries that you're executing on a table, and those queries use different sets of filter criteria, you can potentially require several different indexes to be able to query them efficiently with the columns in different orders. Now, as we've discussed, you don't always want to have lots of indexes because the more you have, the more difficult and the more resource intensive it is to update and insert rows. So with that in mind, Postgres gives you a more streamlined option. It's not as efficient as having specific indexes with all the relevant columns in the right order, but gives you more flexibility and relatively efficient queries with more general indexes. So we're going to look at an example of this. Now, if we have our same data that we were looking at earlier, I've narrowed down our tree, so we only are looking at 8 entries instead of the 20 in our index. But if we have two indexes on this table, we know some of our queries want to query on airport, some want to query on plane class, and maybe we have some that query on both. So we create an index on the plane class and an index on the airport. Now you can see it's pretty quick to come to any particular, airport or plane class. Now, if you have a query that you have these two indexes and you have a query that uses both, so for example, select flight ID from flights where from airport equals YYZ and plane class equals 767, Postgres will allow you to use both of those indexes. And the way it'll do that is it'll walk through both trees. So our first example here, the tree on the left, we're looking for 767. So we look at the first node. And when we look at the first node, we see that it's a 767. And I'm just getting to get my pen open here. Yeah, it's a 767. So great, that's a node we want. Then we navigate down the left-hand side and see that 747. So we know that all of the nodes further on are not relevant for us. They are not 767. So we can entirely get rid of that. And if we know that all the nodes on the right-hand side must be greater than or equal to 767. So we take a look down here. Oh, yeah, we found a 767. That's great. And again, we have to go down both nodes to look at the keys there. And we see 767 and 777. So we don't care about that. So we've identified rows 3, row 6, and row 7 as rows that are potential matches for this query. So what Postgres does is it builds a bitmap, which is really just a list of ones and zeros that are associated with the rows that tells you whether it found a hit for that one portion of the filter criteria. So we see that row 3 is a hit with a 1. We see that row 6 is a hit, has a 1 there, and we see that row 7 has a 1 there. Great. So our bitmap is 001, 001, 10. Then it does the same thing with the other index on airport. We're looking for YYZ. We look at the first key, it's not YYZ, and we know that YYZ must be greater than or equal to YUL, or greater than rather, so we can get rid of that portion entirely. We see the second key is YYZ, so that's one we're interested in. That's great. We have to navigate down to be able to look to see whether any of these are YYZ. They're not, so we don't care about them. Navigate back up and down to the right-hand side, and we find 4 rows that are YYZ. So we've identified 4 rows, 3, 4, 5, and 7, that match this portion of the filter criteria. Postgres builds a bitmap of it. So you can see row 3 is a 1, row 4 is a 1, row 5 is a 1, row 7 is a 1. So our bitmap is 001, 11, 010. Postgres then ANDs those two bitmaps together. So 0 and 0 is 0, 0 and 0 is 0, 1 and 1 is 1, 0 and 1 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1, 0 and 0 is 0. So with ANDing those together, you see that row 3 and row 7 match both criteria. So the results from this particular query tell us to go to row 3 and 7 to fetch the data that we need. So we had to do 2 different index traversals. We had to walk down both, but we were able to relatively quickly build up the right result set and then go and look at those rows. So it's not as efficient as if we were able to just cut out big swaths of the tree if we had an index exactly on airport and plane class, or plane class and airport. But this way you have much more flexibility because you can have several smaller indexes that can potentially be used for a wider variety of queries. All right, so now we're going to talk about the tools that you have to start investigating query performance. So explain is really the key piece of it all. Explain is a tool that's built in and allows you to analyze query performance. It tells you what indexes are used, how tables are joined, and how expensive each step in the query plan is going to be. There are three main ways to execute it. Explain estimates the query plan. So it doesn't actually execute the query. It just takes a guesstimate based on the statistics in the database of what the query is actually going to look like. Explain analyze executes the query and then checks the results and gives you more detailed information about what actually happened. There's also an explain analyze buffers that gives you a little bit of additional detail on the number of reads and writes that take place and how many buffers are updated, deleted, inserted, that sort of stuff. So that's also useful. But explain and explain analyze are really the two key ones. And it's worth remembering that explain, like I mentioned, doesn't execute the query, and explain analyze does. So if you are doing an insert or an update or a delete, you have to be very careful with explain analyze, and you usually want to wrap it into transaction. So if you're executing it, you want to do a begin, execute it, and then roll that back immediately so the changes don't actually take effect, but you can see what it actually ends up doing. And again, the difference between explain and explain analyze is one gives you an estimate based on all the statistics in the database, all that information that Postgres tracks. Explain analyze actually is what the real output would be of the query, how long it actually takes, how expensive it actually is. One of the things you'll note is that if the estimate is drastically different from what explain analyze gives you, then you probably have a statistics problem in your database, and you may need to rebuild those statistics with the tools that Postgres gives you to do that. So let's take a look at the explain analyze output a little bit here. So we can see we are executing a query against our flight database. Explain select flight ID from flights 2 in this case, because I have a table that has more data in it so it actually uses an index, where airport is YYZ and plane class is 737. So we can see that it is doing an index only scan. That's this part here, and that's really interesting. That means it's using a covering index. So we are getting flight ID from flights. Now the index I created for this, because it's on a separate table, I created a covering index that was on YYZ, on the airport and the plane class, and had the include column that included flight ID. So it's doing an index only scan. That's what you want to look for if you're trying to use a covering index. I'll talk about all the things that can pop up there in a little bit. We're going to talk about the generic stuff now. So it tells you what index it's actually using. So in this case, it's using an index called flights2 from plane index covering. So you know what index it actually chose to use. And then we have cost. So there's two cost numbers, and these numbers are made up. They're relative, but they don't actually mean anything in and of themselves. Bigger is worse. So the first number is the estimated cost to give you one row back. The second number is the estimated cost for the entire data set that it's going to be returning. Rows here is how many rows it thinks it's going to return when you execute this query, and width is the average number of bytes per row that it expects it will return. It then shows you below that what criteria it's actually executing the index with. So if it was an index that didn't have airport, for example, you would only see the fact that it was hitting it with plane class here. So it shows you the columns it's actually using against that index. The next section down, we can explain analyze. Otherwise, it's the same query. So you see there's a little bit more information here. Still doing an index only scan. It's using the same index, so that's fine. Our cost is an accurate estimate now. Now, again, it's the ratio that really matters. The numbers themselves don't matter, but the fact that 23.39 is however much bigger it is than 0.42 is the interesting part. So it takes that much longer to return the total result set than the first result. Send the number of rows we return, our estimate was correct, so our statistics are correct, and the width 7. So it actually returned an average width of 7 bytes for all of the rows it returned. Now we get to the extra information. We have actual time. This is time in milliseconds to actually return the first row and time to return the complete result set. We have number of rows returned is 569, so very close to the estimated number, and then loops here is 1. So depending on how the query planner organizes the query, it may execute certain steps of the query multiple times. Loops tells you how many times it executed the particular step we're looking at. Same thing, index condition, we see what conditions were actually applied to the index. And another interesting thing, we see heap fetches right here. Heap fetches is how many times it actually went to the real database table to get information. So in an index-only scan, we should see 0 for this. Now, heap is the Postgres way of saying the actual table. It's not heap in the traditional kind of memory sense of a database. So if you see heap fetches as a number, that means that that number of times it went to the table and actually loaded data instead of loading data from the index. Then you see our row planning time. That tells you how long in milliseconds it took to figure out what to do. So that was when the query planner generated all the possibilities and the cost-based optimizer analyzed them to figure out which ones it was going to execute. And then execution time was actually executing that plan and returning rows. So that is the general idea of the explain query. So I mentioned the notion of loops, how some nodes can be executed more than once. Now, the way this works is the query planner generates the steps to execute as a tree. So it figures, okay, I'm going to do step 1, and then step 1 has one or more child nodes, and each of those child nodes may have multiple child nodes to build the total result. So the top node says, okay, give me a row to all the children nodes. The children nodes then do just enough work to produce one row and no more. And then the parent node says, okay, give me a row. And then the child nodes all do just enough work to give one row or say, no, I don't have any more rows. And that keeps happening until the entire result is returned. So you can see in this example we have here, we have multiple nodes. I'll talk about what some of these details mean in a moment, but our first node is a nested loop join. So this, in this case, we are joining two tables together. So this is the node that is doing that join, and there are two child nodes that it is doing. And both of those nodes are sequence scans. So there is a parent node, the nested loop join, and then two sequence scans where it is actually reading data from the tables being joined and then joining them together. And you can see the top, when you do a nested loop join, the top relation is called an outer table, and the bottom relation is called the inner table. So in the outer table, it did one loop. It read through the rows on the first table, and then it had to do two loops of the bottom one. So there's actually two rows in the table that in the first table that it was having to compare against. So we see it executed this node twice and this node once. And again, we see our planning time and our execution time. Okay, so there's a number of scans you may see in that node. I'm just going to jump back for a second. You see we have sequence scan here, and in the previous slide, we also saw our index only scan, right? So there are a number of those scans that you can have, and we're going to talk about them. So a sequential scan, or a seq scan, as it's listed in the explain output, is what's otherwise known as a full table scan, a sequential scan. This is where it's reading every single row in the table. It's going to go from the top, read through till the end, touching every single row, every single page on the disk. This is the most inefficient way, usually, of reading data from a table, but sometimes it's the only option. It will always work. So that's what the fallback will be. If you have a very large table and you see a sequence scan happening, that's a key indication that you have not created the right indexes. So next is an index scan. So this is when you have an index that you are using. So your query matched an index, and the cost-based optimizer figured there is a particular index that will cut down a significant number of rows. So that's great. It looks at the index like our examples where we walked through the BTrees, builds up a list of row IDs, and then goes and does heap fetches where it actually reads the real data from the table. So generally very, very efficient. Index only scan is when it is only using the index. So that's the covering index, when it's able to return all of the data from the index itself. So that's great. That is very, very efficient. Now, before I move on to the next two, I want to mention just a couple little details about the two first ones, sequence scan or sequential scan and index scan. So if you have a table with 1,000,000 rows and you execute a query that's going to return 999,000 of those rows, obviously, even if you have a fantastic index, it doesn't make any sense to use it because you're reading through the entire table. So if you hit an index, it would just slow you down because you are hitting the index, finding a row, reading the table, hitting an index, finding a row, reading the table, doing that for almost every single row. So you're almost doubling the IO operations. So if you're going to read almost every row from a table, then it's going to ignore an index. So if you are going to read all the rows or you have a very, very tiny table, a sequential scan will be used and is actually a good thing in those scenarios. It's when you have a lot of rows and are trying to only return a few rows that you don't want to see a sequence scan. Index scan is great when you have a few rows that you're being returned. So ideally, as I mentioned, you have to hit the index, look up a row, go look up the actual row in the heap, and then do that a few times. This index scan will ideally be used when you have a large table that you are only trying to return a few rows on. So then we move on to these bitmap items, bitmap index scan and bitmap heap scan. So this is the in-between option. So when you have a large table and you're returning a substantial number of rows from it, but not most of the rows, and more than just a few. We talked about bitmaps earlier in the context of using multiple indexes for a query, combining indexes, and this is kind of the same principle. What will happen is it'll discover an index that it can use. It will walk through that index, finding all the relevant rows, and rather than immediately going to the actual table to read those rows, it generates a very large bitmap of all of the relevant rows. It's able to filter that using the visibility filter we talked about earlier, and then it'll execute a bitmap heap scan. So you'll always see these two nodes together, a bitmap heap scan on top and then a bitmap index scan below. And a bitmap heap scan is when it just applies the bitmap that is built from the index scan to the actual rows in the table. And the goal here is that you are able to read large chunks of the disk at a time. So if you're returning, say, half of the rows in a 1,000,000 row table, and it's well indexed, odds are every disk page is going to have several rows that you want. If you are doing an index scan, you find a row, go load the page from disk, find the next row, go load the page from disk. Odds are it's not going to be on the same page. And keep doing that. You're going to get different pages each time, and eventually those pages will flush out of the cache. However, with the bitmap index scan and bitmap heap scan, once you have that giant list built of all the rows you care about, then you figure out, okay, I'm going to look at all the rows that are on the first page on the disk. I'm going to load that page. I'm going to read all those rows. Then I will load the second page on the disk, look at my bitmap, and read all of the rows from the table that are on the second page, and keep doing that. So in that way, you're not bouncing back and forth all the time. You pre-calculate a list of all the rows you need, figure out which parts of the disk they're on, and then load all of the rows from that portion of the disk when you actually need them. So it's a middle ground. Bitmap index and heap scans are for when you have a large table that is indexed and you're returning a medium number of rows. Index scan is great for when you have a large table that's well indexed and you're returning a small number of rows. And a sequence scan is what you're going to see if you have a very tiny table or you have a large table where you're returning almost all of the rows. Now, we saw the nested join loop in the explain output that we looked at. There are three kinds of join strategies that the database is going to use that you're going to see in that explain output. And each of them have different pros and cons and are used for different things. So the one we just looked at is the nested loop join, which is the most general join. It has the worst performance overall, but it works in all situations. So the other ones are more specialized, but it will fall back to a nested loop join. Now, we mentioned that there is a notion of an outer relation and an inner relation in a nested loop join. And you can see that here, the top one is the outer and the bottom one is the inner. And as I kind of walked through when we talked about it, a nested loop join reads a row from the outer table and then goes and loops through the entire inner table, possibly using filtering to find the rows it needs, and then returns them. Then it looks at the second row in the outer table and then loops through all the rows in the inner table, and so on and so forth. That's why it's a nested loop join. So if you have an index or any combination of indexes on the outer relation, they will not help at all. So it doesn't matter what indexes are on the outer relation. If you have an index on the inner relation join key, that will be useful. It will be able to filter down the rows. So that's ideal. The issue is, it's not inner and outer in terms of, you have an outer join and an inner join. It's just outer in terms of the table it chooses to look at first, and inner is the table it chooses to look at second. If you have a join criteria of table, from table A, join table B, there's no guarantee which one is going to be the outer and the inner. It's whichever one the cost-based optimizer thinks is the best option. So whichever one it chooses to be the inner, an index on the join key will be very helpful. The next join is a hash join. And this is good for medium-sized result sets. The one issue is you require an equality condition. So if you do a join where you have, from table A, join table B, where A dot some column is greater than B dot some column, that's an inequality relation. So a hash join will be totally useless for that. You have to have at least one equality condition. A nested loop join would work for that, but a hash join will not. And the idea with a hash join is it generates the results from both of the tables that are being joined and then builds up a hash map, very much like a hash map in memory if you're thinking of a programming language. So it takes the key, hashes it to a 32-bit value, and then maps that, ideally in memory, to a row ID. Does that for both of the tables being joined, and then literally just iterates through one and looks up in the hash map the specific row in the other one. Ideally, you'll want both hash maps to fit into memory, but if one table is larger and one is smaller, you want the smaller table to be able to fit into memory. If neither of them fit into memory, then you're going to get slow performance because it has to actually write them out to disk as it's building them, and that can be a problem. Now, if it chooses to do a hash join, if the cost-based optimizer chooses to do a hash join, indexes are not useful at all. So if that's the strategy it selects, doesn't matter what indexes you have on that table, they will not be useful to improve the join performance. Now, the last one is a merge join, which is great for joining large tables, and it's almost a kind of special case of a nested loop join. It only works if you have an equality condition. Again, it won't work with greater than or less than join conditions. One of the conditions has to be an equality condition. And the join keys have to be sorted. So the table has to be sorted on the join keys. If they're not, by default, then it'll write a temporary table for each of the tables in a sorted order. And merge join is like a nested loop join, but everything is sorted. So in the outer relation, you find a row. In the inner relation, you seek to where the join starts. You read all of the rows until they no longer match. Then you go back to the outer relation, go to the second row, and then you know that because both are sorted, your position in the inner relation starts right where you left off. So then you can just read a contiguous chunk until you no longer get a match, and then go back to the outer join. So it's a nested loop join, but you know where to start in the outer relation, and you're able to scan contiguous chunks. So those are the only three you will see there. Okay, so can you trust the explanation? Doing explains is a little bit of an art because of the statistics I mentioned. So you have pretty more or less four scenarios when you're doing explains, and they give you different level of quality results. So the absolute best way, if you want to figure out what the query plan is that's going to be executed, understand the performance, and figure out how to optimize a query, is doing an explain analyze on a production database. This gives you the actual data because it's in production. You see the actual query plan, not an estimated one, and it uses the actual statistics, so nothing can go wrong. This, of course, can impact production because it actually executes the query. If it's executing a select, it may read a lot of data that can slow your database down. If it is doing an insert, update, or delete, then it can obviously mutate your data, so you have to do it in a transaction. And inserts and updates can be slow as well. So that can have an impact. But you get the best results. You get 100% certainty what the query plan is and what the impact is going to be. The impact is going to be on your database. So the next best option is just running an explain in production rather than explain analyze. So you're doing it on the actual data, which is great, and you're doing it with the actual statistics, which is great. So it's giving you probably a pretty close estimate of what's actually going to happen if your statistics are up to date. It's only an estimated plan though, so there still could be differences, and it doesn't have any performance impact on production. So it's the next best. If you can't do an explain analyze because your database is on fire and you don't want to risk actually putting more load on it, explain is the next best thing to do. After that, your next best thing, or good in this case, is an explain analyze on a local copy of real data. So this is where you get a production database dump restored on your database on your local machine, or on a QA environment or staging environment, something along those lines. You have the actual data, so that's great, but your statistics are not. Your statistics, it will give you the number of rows, for example, but they won't have information on the usage patterns of the table and the query patterns. And that's an important part of figuring out the right query plan to execute. So you'll get an estimated query plan, only partial statistics, but you'll have the actual data. So it's less accurate, but for most use cases, it's good enough to make sure that, generally under these set of circumstances, with this amount of data, this query plan will probably be used. So that's usually good enough if that's all you can do. And then our worst case scenario, if it's all you got, and explain, analyze on synthetic data. So this is where, okay, I have a table, I know the structure, I'll just insert a million random rows into it. Or, if I have 10 million rows in production, I'll insert 10 million random rows. So it's fake data. You get fake query plans and fake statistics. You have no idea whether this is right or not, and whether it actually resembles what's going to happen in production. It gives you hints, like you could see, okay, well, if I have this much random data, it does choose to use this index, and it improves performance from X to Y. But you don't know if it's actually going to choose that in production. But it gives you, a step in the right direction if that's all you have. So you have to make do with what you got sometimes, and that is an option that can give you some information. All right, so what are some concrete steps that you can take to develop better indexes and increase performance? So we mentioned statistics a whole bunch of times. There's a command in Postgres called analyze. Now, before you do any query optimization or performance analysis, you should run analyze on the table name that you're going to be analyzing. And that ensures that all the statistics are up to date. It's also a good idea to do a vacuum ahead of time if you can, to clear up any garbage data that's laying around, and then do an analyze. It'll build up the statistics. This is particularly critical if you're doing a local copy of real data or synthetic data. You just insert the data, the statistics may be totally out of whack. So you're going to force it to update the statistics. Then you want to list all the queries that you're potentially going to be executing against the table. You want to look for commonalities in your filtering columns and your join columns. You want to, see if there are common usage patterns. And then you want to figure out what the most expensive queries probably are. Which ones return the most rows? Which ones filter on the least number of things? So they're likely to, return large data sets. You want to explain analyze each of those queries to see how they work today. You want to look at the cost of the various steps, both the cost of time to first row and the cost of the time to the complete data set. Pick the largest ones of those, the largest nodes, and then work on optimizing those. We've talked about the different kinds of scans and the different kinds of joins it may use and which types of tables and which sizes of result sets they're good for. So if your query pattern and the results you're expecting is, matches one of those criteria, and you're not seeing the appropriate, whether it's sequence scan, bitmap scan, or index scan, then you want to look for indexes that will allow you to actually achieve that. You don't want to generally add indexes to small tables unless it's for the purposes of being a primary key or a unique key. They're fine for that. But again, the more tables or the more indexes you add to tables, the slower it is to update. And indexes on small tables will generally not be used because it's easier just to read the whole table. So avoid indexes on small tables if possible. So if you're creating multi-column indexes, those composite indexes we talked about, when you are deciding on the order of the columns, use the filter criteria for your queries as a guide. However, if you have a choice between two orders that are look like they'd be equally appropriate for most of your queries, the first one, the first column should be the one that filters out the most rows. So if you have a table with 1,000,000 rows, and an equality condition on the first column will filter out 900,000 of those, and an equality condition on the second one would filter out 500,000 of those. You want to use the one that would filter out the most, so the 900,000 in that case first. That lets you cut off the largest portions of the B tree and give you the fewest nodes and keys that you have to walk through in your index. So you want to remember that the leftmost equality conditions and the first inequality condition can be used to ignore unneeded parts of the index. But if you have a query that doesn't do an equality condition on the first part of the index, but does an equality condition on the second column or an inequality condition, it won't be able to cut out those parts of the index. So it's really important to filter on the leftmost sections of the index and move from there further right. Also, don't blindly add indexes. Test, use your explain, analyze, add an index, test some more, see what the improvement is, see whether you're getting the kind of scans and this kind of queries and the kind of joins you expect to get. And if not, look at adding a different index. So don't just say, okay, well, I have these 10 columns and I query on them a lot, so I'm going to add a single column index on each one. Almost guaranteed that is a poor choice. Even with the notion of combining composite or combining indexes, you don't want to just blindly index everything. Use your indexes wisely. Figure out which ones are most appropriate and add them, and then monitor. Make sure that you're continuing to get good performance. And then finally, be careful when you add indexes to write-heavy tables. So as we mentioned, if you have an index, it has to be updated every time you insert, update, or delete. If you have a table in a database that's on fire because you're writing so much, and you add a bunch of indexes to that table that is, experiencing so much write load, you've just increased the write load and made the database suffer even more. So you have to be very, very careful, depending on the workloads of the table, what indexes you add. So as I mentioned, all of this is a little bit science, a little bit art, a little bit experimentation. You can generally deduce from looking at your queries in the table structure what some good indexes are likely to be. Test it out to make sure you're right, but then continue to test and iterate to make sure that you're getting the performance that you need. And I've included a bunch of links for further reading here. Like I said, all this information is easily available, but putting it together can be a little tricky. So here are some resources I would suggest you check out. First, of course, is just the Postgres indexing docs. So everything I've talked about as far as indexing and Postgres goes is in the indexes chapter of the Postgres online docs that you can see. Doesn't have the examples and walking through what B-trees look like or anything like that, but it gives you the overview of all of this stuff. There's also a link to the Postgres MVCC docs where you can learn more about how row visibility works, how transaction isolation works in Postgres, and figure out how that actually impacts indexes. There's a great website, pganalyze, that gives you information on all the things that will show up in an explain query. So this is where I generated that information about the nested loop joins and the merge joins and the hash joins and all that sort of stuff. It's all there. Anything you can find in an explain query shows up there with a brief explanation. You may need to go digging a little more to find the real details, but it at least points you in the right direction. There's a great website, Use the Index Luke, that is DB agnostic, and it just goes through kind of all details of all indexing strategies and things you want to look for. It's a great reference site. Everybody should check it out. There's a great website, Cybertech PostgreSQL, that just talks about all sorts of Postgres tips as far as performance goes. So it's one of the first places I'd go to if you want to learn about making Postgres queries more performant. And then lastly, while I was building all of my B trees for my examples, I used this particular website here, which is just a B tree visualizer. So you type in numbers and it creates the associated B tree based on the values that you say are the maximum values you could have in any one node, and it shows you how it's actually building. So if you want to go to that website and play around with adding some in, you can see what indexes or what B trees actually look like when they're being built and how they actually work. So that is it for me, thank you very much for joining me and for sticking through all of my very lengthy examples. I hope this has been a useful discussion for you. Again, this is all very high level. This is kind of introduction to indexing. There's more detail and a lot more depth you can get into. Postgres particularly has a lot of complicated use cases that even go beyond the stuff I've talked about. So when you look at subqueries, indexing those is a little trickier. Common table expressions, things like stored procedures throw a little bit of a wrench into the works. So, you get a few extra complexities. This gives you a general introduction, and I'm hoping now you can go look at, some of the more detailed stuff depending on your specific use cases. Again, we didn't cover some of the other types of indexes that are in use, but now that you have a general idea of how B-trees work, I think you're better prepared to go and actually investigate the details of the Brin index and the Gin index and the generalized search tree indexes and see how Postgres makes querying all sorts of other data types efficient. So thank you very much for joining me. Have a good day.